Greetings again. Another assignment and quiz are in the books, and I trust you mastered both of them. Before I begin today's lesson, I want you to remember a little tiny something from sections 3.1 and 3.2. Section 3.1 had a postulate and a group of theorems that all went something like, if two parallel lines are cut by a transversal, then something was true. The next section, 3.2, had a postulate and a group of theorems that were basically converses, that if such and such is true, then the lines are parallel. The theorems in sections 6.2 and 6.3 have a similar sort of relationship. In section 6.2, the last section, we would be given that if this is a parallelogram, and then something would be true about it. Today, in section 6.3, we'll see some converses, that if something is true, then this is a parallelogram. But first, let's review what we know about the characteristics of a parallelogram. The first and most obvious comes from the definition, not a theorem, that both pairs of opposite sides are parallel. We then had theorems that told us all the rest. Both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent. We also know now that the diagonals bisect each other. And finally, we know that any pair of consecutive angles is supplementary. Now, if we have a parallelogram given to us, we know that all 5 of those things are true. Today, let's prepare to move in the opposite direction. Let's head to page 263 and get started. The opening question of this lesson asks, on page 263, what characteristics of a quadrilateral are sufficient to show that it is a parallelogram? In other words, what has to be so for some quadrilateral to be definitively classified as a parallelogram? We're going to see 5 answers to that question today, the first of which we saw earlier in the chapter in the definition. We will know that a quadrilateral is a parallelogram if it has 2 pairs of opposite parallel sides. This is not a theorem, and it doesn't need to be proved because it's the definition. That's what a parallelogram is. If you ever spot a quadrilateral with 2 pairs of parallel opposite sides, it's a parallelogram, period. Now, if you're still on page 263, though, you'll see that we are rapidly presented with 4 theorems that also answer the question about how we know some quadrilateral is a parallelogram. Let's start with the first one. This theorem tells us that a quadrilateral is a parallelogram if both pairs of opposite sides are congruent. Now, this sounds exactly like the converse of theorem 6.2.4 because, well, it basically is. Now, I've used the example in the past with my students that a parallelogram looks like a rectangle that somebody kicked and, knocked out of alignment. Now, that's not a very good geometric description, but nearly everybody recognizes that a rectangle has opposite sides congruent. It just happens to also have 4 right angles. Now, back to the theorem. The diagram gives us a quadrilateral with both pairs of opposite sides congruent. Notice that a diagonal, BD, is added as an auxiliary line. Now, it's pretty easy to show that the 2 triangles are congruent by side, side, side. Angle 1 and angle 2 are corresponding angles, and therefore congruent, and because they are congruent, sides AB and CD are parallel. Notice that BD functions as a transversal, with angles 1 and 2 being alternate interior angles. Angles 3 and 4 are likewise congruent corresponding angles, and as alternate interior angles, they help to prove that sides BC and AD are parallel. Consequently, with both pairs of opposite sides parallel, ABCD is a parallelogram. Now, what I basically just did there was restate the paragraph proof found on page 263 of your textbook. The paragraph proof is concise and accurate. We could take the time to rework it into a 2-column proof today, but I decided instead to dedicate our time elsewhere. Besides, by now, I'm increasingly confident you could do that yourself. Now, let's look at the next theorem. This theorem tells us that a quadrilateral is a parallelogram if one pair of opposite sides is both parallel and congruent. Notice, the same pair has to be both parallel and congruent. The diagram is marked accordingly, with sides AB and CD being parallel and congruent to each other. You'll also notice an auxiliary line, a diagonal again, that divides the parallelogram into two triangles. If those triangles are congruent, as it appears they may be, you could complete this proof without difficulty, because all you would really need to gain is that sides BC and AD are congruent. Its conclusion is quite similar to the last theorem. Consequently, we're not going to prove this one right now either. I'm thinking about including it on today's assignment. Just be comforted that it really is about as easy as the previous theorem. Notice, too, that this is the only theorem in the group that is not a converse of one of the theorems in section 6.2. So now we have three ways to prove a quadrilateral is a parallelogram: the definition and these first two theorems. Now let's look at the very next theorem, which we are going to prove together. This fourth way of proving a quadrilateral is a parallelogram is if both pairs of opposite angles are congruent. Now this may not surprise you, since you learned that if a figure is a parallelogram, then both pairs of opposite angles are congruent. And you'll notice, as usual, that I included a diagram to illustrate this theorem. And perhaps you're thinking, he's going to draw another auxiliary diagonal and prove the two triangles are congruent, blah, blah, blah. Not this time. The proof actually avoids that and uses a very different approach. And that's why we are going to prove this one together. The given is already in place, that the two pairs of opposite angles are congruent. Angles A and C are congruent, and so are angles B and D. A second statement follows quickly from the first, that the measure of angle A is equal to the measure of angle C, and the measure of angle B is equal to the measure of angle D, and this comes from the definition of congruent angles. The third statement is the one that you might not be expecting, and it is that the sum of all four angle measures is 360 degrees. We know this from the quadrilateral angle sum theorem. Now you might be wondering, why would we use that, or where does that come into play? Good questions. We're going to use a little bit of algebra now to reach another helpful conclusion along our way. The fourth statement takes advantage of statement number 2 by substituting the measures of angles A and B for the measures of angles C and D. That should be pretty easy to see. The fifth statement is basically a combining of the like terms with the 2 factored out, and it's the distributive property that allows you to factor out that 2. We then divide both sides of number 5 to get statement number 6, which is that the measures of angles A and B add up to 180 degrees. And as you know, the multiplication property of equality applies to dividing as well. Now, since angles A and B are supplementary, and since they are consecutive interior angles, that means we have 2 parallel sides, AD and BC, and those are, in fact, our next 2 statements. Statement number 7 is that angles A and B are supplementary from the definition of supplementary angles, and statement number 8 concludes from that sides AD and BC are parallel. This comes from the theorem that says if the consecutive interior angles are supplementary, then the lines are parallel. That's theorem 3.2.3. We repeat this process to show that the other sides are parallel. Statement number 9 uses a substitution of angle D for angle B to say that the measure of angle A plus the measure of angle D equals 180 degrees. Now, similar to before, this means that angles A and D are supplementary, again, from the definition of supplementary angles, and as a consequence of that, sides AB and CD are parallel by the converse of the consecutive interior angle theorem. Now, the 12th and final statement is that ABCD is a parallelogram by the definition of a parallelogram. It has 2 pairs of parallel sides. So yes, that proof was quite different from the first 2 that we looked at. We still have one more way to show that a quadrilateral is a parallelogram, and it is the final theorem listed on page 263. This one says that a quadrilateral is a parallelogram if its diagonals bisect each other. This also sounds a lot like a converse of a theorem from the previous section. Now, the proof of this one is also buried back in the exercises. We're going to start it together, but I'm going to ask you to finish it as part of your assignment. This is the diagram we'll be using. The given is based on the if its diagonals bisect each other, which, by the way, is still the hypothesis of the conditional, even if grammatically it comes at the end. The diagonals are AC and BD, so the given is segments BD and AC bisect each other. The proof, as with the other theorems we have looked at today, is that ABCD is a parallelogram. Okay, so here we get started. The given, as we all know by now, comes first. The second statement is that point X is the midpoint of segments BD and AC because of the definition of a segment bisector. And of course, this means we have congruent segments, specifically AX and CX, and BX and DX by the definition of a midpoint. Now, if you were taking notes on this, as I hope you are, and especially since I mentioned that little something about the assignment, I encourage you to mark your diagram with those congruent parts I just mentioned. If you do that, the very next statement will be moderately obvious and will have something to do with congruent vertical angles. But I'm going to leave it at that and allow you to finish that proof on your own. Over on page 264, we have example 1. In each of the three parts of example 1, you are asked to determine whether the quadrilateral pictured can be shown to be a parallelogram and to explain your reasoning why it is or is not. Instead of those examples, though, I'm going to give you a few of my own selecting. Same instructions, different diagram. Here's the first one. Notice that this quadrilateral has two known angle measures. One is 68 degrees, and the other is 112 degrees. Is this a parallelogram? Yes or no? I realize those two angle measures add up to 180 degrees. But this is not a parallelogram because two pairs of supplementary consecutive angles are required. This is actually a trapezoid because it has one known pair of parallel sides. Here's the second one. This quadrilateral has some congruent segments marked. Is it a parallelogram? And this time, the answer is yes, because those two diagonals bisect each other, and our last theorem applies here. Here's a third one. Look very carefully at what's marked on this one. Can we conclude that this one is a parallelogram? Well, if you said yes, you're right, because the top and bottom sides are both parallel and congruent, and one of our theorems applies directly here. Now, as a final example to look at in this lesson, skip down to example number 3, the bottom of page 264. What you see there is a pair of parallel pliers. Here on my desk, I have a pair of cheap, regular pliers. Now, they do the job, but look closely at the business end here. The two gripping parts right here have flat surfaces. But as I open and close them, notice that these surfaces are no longer parallel to each other. Now, there are a lot of other types and sizes of pliers available at local stores, but most of them have this same issue. The jaws here at the end do not remain parallel to each other. The drawing with example 3 shows the basic design of parallel pliers. Now, points A and B are where one jaw is connected to the handle, and points C and D are where the other jaw is connected to the other handle. Point X serves as the fulcrum, and point X is strategically located so that it is the midpoint of both AD and BC, and since segments AD and BC bisect each other at midpoint X, the quadrilateral formed by connecting A, B, C, and D must therefore be a parallelogram, and AB and CD must therefore be parallel to each other. And this is what keeps the two jaws parallel to each other. X is still the midpoint, regardless of where the handles are positioned, open, closed, or anywhere in between. Now, I learned as I prepared for this class that you typically have to special order this kind of pliers because many stores do not keep them in stock. So I don't have a pair to show you, or to use myself at my own house. But we're going to pause in our progress here, and we're going to complete section 6.3 in the next lesson. Your assignment is going to include most of the problems on page 266 plus number 26 and number 27 on page 267. We started number 27 during the lesson video, so feel free to copy what we saw together and pick up where I left off. Now, in closing, let me show you one question from the exercise set, one which is not going to be assigned today. Question number 15 shows this piano keyboard on a stand and states that the two legs of the stand, which are adjustable, are connected at their midpoints, and it asks you to explain why the keyboard remains level to the floor as the stand is raised or lowered. The answer is because the floor and the keyboard function as opposite sides of a quadrilateral, and since the diagonals, the two legs of the stand, bisect each other, there must be a parallelogram here with the keyboard remaining parallel to the floor, which is the point, of course, as any pianist knows. Who'd want to play a piano with an unlevel keyboard? By the way, ironing boards work on exactly the same principle. Scissor lifts also use this principle with what amounts to a stack of parallelograms. Welcome back to another exciting lesson in geometry. Your assignment should have been completed by now, including those two proofs at the end. I want to start today by paying special attention to number 27 from the assignment. You had to prove the theorem that says a quadrilateral is a parallelogram if its diagonals bisect each other. I showed you the first three statements and reasons in the last lesson, and here they are again. The given was that the diagonals BD and AC bisect each other, and that led to the two congruent pairs of segments in statement number 3. Now, if you marked the diagram as I suggested, you can probably guess that the vertical angles come next, and you'd be right. The answer key points out that both pairs of vertical angles are congruent. And the fifth statement identifies two pairs of congruent triangles, which are named on the screen, and congruent by side angle side. Statement number 6 is key because it shows the corresponding congruent parts, CP, CTC, as we usually abbreviate it. Now find those angles on the diagram, and then notice that each pair is a pair of alternate interior angles in the diagram. The diagram now indicates the congruent angles from statement number 6. Statement number 7 points out that the sides are parallel because the alternate interior angles are congruent, and the last statement is our proof, with the simple reason of definition of a parallelogram. It's really a nice, tidy little proof, but it's actually just one way to prove the theorem. It came right after number 26 in the exercise set, and there is another way to prove number 27 using the theorem 6.3.2 in number 26. So now I'm going to show you a second way to prove this theorem in number 27. The first three statements and reasons would be exactly the same. But remember, a quadrilateral is a parallelogram if it has one pair of opposite sides that are both congruent and parallel. So for the fourth statement, we're only going to need one pair of vertical angles to be congruent, and those are angles BXC and DXA. For the next statement, we will have one pair of congruent triangles, BXC and DXA, by the side angle side congruence postulate. For my next statement, I will point out that the third sides of both these triangles, BC and DA, are congruent by CP/CTC. Now remember where we're going with this. We need one pair of opposite sides to be congruent and parallel. Now we have this pair of opposite sides congruent. Next, we need to show that they are parallel. So our seventh statement will be to identify another pair of congruent parts, and this time angles XBC and XDA. Notice that these two angles are alternate interior angles, and therefore sides BC and DA are parallel. And finally, since segments BC and DA are both parallel and congruent, we can conclude that ABCD is a parallelogram by theorem 6.3.2. And notice, two different proofs of the same theorem. Either one of them would have been perfectly acceptable as an answer to number 27, and if you had a third variation that was also logical and complete, that could work too. So now that we've had this lengthy introduction, let's pick up where we left off in section 6.3. We saw in the first part of this section that there are 5 ways to conclude that a quadrilateral is a parallelogram. The first is to use the definition. It has 2 pairs of opposite parallel sides. The other 4 ways are theorems, each of which has been proved. Examples 1 and 2 give us a little practice with those theorems, so let's look at them now. Here we see a quadrilateral. It has 2 congruent sides, DG and EF. And, oh, by the way, we're also given 2 of its angle measures. So is this a parallelogram? It's not as obvious as some of the other questions, but the answer is yes. Those 2 angles are supplementary, and when the consecutive interior angles are supplementary, there are parallel lines, and when the parallel sides are also congruent, theorem 6.3.2 applies. Now let's look at 1b. This quadrilateral has 2 pairs of congruent angles. Is it a parallelogram? Not this time, because the relevant theorem states that both pairs of opposite angles are congruent. These congruent angles aren't opposite each other. However, this is a trapezoid, because you can easily show that sides KL and JM are parallel. This third one has a pair of right angles. Is it a parallelogram? Again, the answer is no, and for the same reason. We need 2 pairs of opposite angles to be congruent. However, like part B, we again have a trapezoid. Now there are several questions like this in the exercise section, as you've probably discovered by now. Let's move along to example 2a. Its instructions tell us to find the value of each variable that ensures that the pictured quadrilateral is a parallelogram. So here's example 2a. Notice that it's the diagonals that are labeled, and for this to be a parallelogram, the diagonals must bisect each other. Consequently, if we look at diagonal QS, the 5a must be equal to 20. Now, solving that is rather simple. We divide both sides of it by 5, and we get a equals 4. The other diagonal is similarly dealt with. For this to be a parallelogram, 6b plus 2 must be equal to 7b minus 4, and solving this might take a few seconds longer, but we should get b equals 6. So, if a equals 4 and b is 6, then PQRS is most definitely a parallelogram. Example 2b shows you a quadrilateral with algebraic expressions for each of its side lengths. However, this one requires a little more work than example 2a did, because the opposite sides don't use the same variables. Nevertheless, it can be done. For this to be a parallelogram, the opposite sides, both pairs, must be congruent. That means that x plus 11 must be equal to y, and 2x must be equal to y plus 14. Now this is what we call, in algebra, a system of equations. And while there are several ways to solve a system of equations, I'm going to use the easiest one here, substitution. And I'm going to use an even easier way than the book uses, by substituting the y with x plus 11. So that will give me 2x equals, and then I replace y with x plus 11 plus 14. Now I'm going to subtract x from both sides, like so. And so I'm going to get x on the left, and then when I combine 11 and 14, I get 25. So x is equal to 25. To find y, I simply go back and put the x in there, and y is going to be equal to 25 plus 11, and that's 36. And so for our total answer, our final answer, x is equal to 25, and y is equal to 36. So for that example, if x equals 25 and y equals 36, that figure is a parallelogram. Now over on page 265, we are introduced to two more theorems. Both of them deal with polygons that are congruent. Now remember that back in chapter 4, we saw a whole group of postulates and theorems that talked about triangles being congruent. Now same sort of idea here, but with polygons. The first one is called the polygon triangulation theorem. For this to be a parallelogram, the opposite sides, both pairs, must be congruent. That means that x plus 11 must be equal to y, and 2x must be equal to y plus 14. Now this is what we call, in algebra, a system of equations. And while there are several ways to solve a system of equations, I'm going to use the easiest one here, substitution. And I'm going to use an even easier way than the book uses by substituting the y with x plus 11. So that will give me 2x equals, and then I replace y with x plus 11 plus 14. Now I'm going to subtract x from both sides, like so. And so I'm going to get x on the left, and then when I combine 11 and 14, I get 25. So x is equal to 25. To find y, I simply go back and put the x in there, and y is going to be equal to 25 plus 11, and that's 36. And so for our total answer, our final answer, x is equal to 25, and y is equal to 36. So for that example, if x equals 25 and y equals 36, that figure is a parallelogram. Now over on page 265, we are introduced to two more theorems. Both of them deal with polygons that are congruent. Now remember that back in chapter 4, we saw a whole group of postulates and theorems that talked about triangles being congruent. Now same sort of idea here, but with polygons. The first one is called the polygon triangulation theorem. The theorem says that two polygons are congruent if they can be divided into congruent corresponding triangles. Now you might wonder what that looks like. Suppose we wanted to prove these two pentagons congruent. If you could divide them up into triangles and then show that each of the three triangles on the first pentagon is congruent to its corresponding triangle on the second pentagon, you could then conclude, based on this theorem, that the pentagons are congruent. Now, the theorem applies to all polygons with more than three sides. Because of that, its proof requires techniques that we haven't learned yet, and so you'll just have to trust me that a perfectly good proof really does exist for it. Speaking of perfectly good proofs, let's move to example 4. In this proof, we are given that both ABCD and PQRS are parallelograms, which does impart a lot of other usefulness too. Notice that there are already some congruent items labeled. Those are also part of the given. You'll see them in the first statement. We are to prove that the two parallelograms are congruent. It should also be noted that we have an auxiliary line, a diagonal, in each quadrilateral. Now, since the complete proof is in your book, I'm going to do something a little bit different this time. I'm going to put the diagram back up on the screen and talk through the proof, almost like a play-by-play announcer. You'll have it all in your book, and you should keep that handy as I describe the steps. The given, as you already know, is that these are both parallelograms, and that segments AB and PQ are congruent, and segments AD and PS are congruent, and angles A and P are congruent also. Now the two auxiliaries are diagonals of each quadrilateral, and the line postulate allows us to have them there. So right away, we can see that triangles ABD, okay, that's this one here, ABD, and PQS are congruent. All right. Now, they're congruent by side angle side. Now, since those triangles are congruent, the fourth statement is that segments BD and QS are congruent. Okay, so BD, QS. Statement number 5 is where it gets fun. Since both figures are given to be parallelograms, each pair of opposite sides is congruent. So I'm going to mark them all. AB with DC, okay, and PQ with SR over here, and AD with BC, and PS with QR. All right. Now, by this point, you should be wondering if we maybe have some other congruent triangles, and we do. Statement number 6 just uses the transitive property or some creative substituting to name the corresponding pairs. And statement number 7 gives us that the other pair of triangles, BCD and QRS, are congruent. Then the last statement tells us that the two parallelograms are congruent by the theorem at the top of the page. So now that we've finished that example, let's note the other theorem on page 265, the SAS congruence theorem for parallelograms. Here's what it says. If two consecutive sides and an included angle of one parallelogram are congruent to two consecutive sides and an included angle of another parallelogram, then the two parallelograms are congruent. Now, two things to notice here. First, this theorem applies only to parallelograms and not to other polygons or even other types of quadrilaterals. And second, as with triangles, the congruent angles must be the angles included between the pairs of congruent sides. So maybe you're wondering, is he going to prove this one on the video? Or is he going to make us do it for our assignment? Or is he going to maybe skip it all together? Actually, it's already been proved. Example 4 is, in fact, the proof of the SAS congruence theorem for parallelograms. Notice the given was that we have two parallelograms and some side angle side parts that were congruent. We proved that the parallelograms were congruent. That's all we need. Example 4 is the proof of this theorem. And that means we're done. No, really, we've reached the end of section 6.3, so it's time to discuss the assignment for today. Today's problems will come from page 267, including one proof at the bottom of that page. Now, you will need to pull out your algebra skills to solve a few systems of equations today, but the review will be good for you. By the way, one of the diagrams has an extra angle label that you won't use. Don't let that fool you. Finally, if you skip back to number 36 on page 268, you will see a very interesting theorem. We're not going to prove it together, although we could, but I just like to point it out because it's neat. Now, it probably could have been a numbered theorem in our book, but the authors decided to place it here. Basically, you have a fairly random convex quadrilateral, and the midpoints of the sides are drawn and consecutively connected. We can prove that the midpoints are the vertices of a parallelogram. And this is true no matter what the original convex quadrilateral is. Think about that. You take any quadrilateral, draw the midpoints of the sides, connect them in order, and you have a parallelogram. And that's pretty neat.